Hi, and welcome to the SAME Environmental Committee webinar, Innovative Techniques in Creating Long-Term Solutions for Large Groundwater Plumes. My name is Nicole Matthews, and I'll be available to assist with most technical issues that may arise. If you have trouble connecting, please email me at nmatthews@same.org, or you can call WebEx directly at 1-866-779-3239. You can also send a direct message via the Q&A box located at the bottom right of your monitor. During the presentation, please submit all your questions for our panelists through that Q&A box and send to all panelists. Please address which panelist the question is for. Finally, the webinar is being recorded. A link to the recording will be made available to all attendees within 3 business days. Thank you for your participation today, and I will now hand it over to our moderator, Jim Romer.
Well, good afternoon. Appreciate all of y'all taking time out of your day to join us. I'm Jim Romer. I'm a principal engineer and regional remediation practice lead for AMEC Foster Wheeler, and I'll be your host for today's webinar. I also serve as remediation lead on the SAME Small Environmental Committee, who's representing or sponsoring this webinar today. And just, so y'all know, the mission of the Environmental Committee is to enhance professionalism and create value both for the civil service and the military members, and to provide, true training and informed exchange of ideas like today's webinar. We try to get guest speakers on relevant topics during monthly conference calls and support promote environmental awareness and committee objectives, and we'll also be at the Joint Engineer Training Conference and Expo JETSI in Columbus, Ohio here next month, and be looking forward to hopefully talking to some of y'all then and trying to recruit for new members. In an effort to focus on current challenges that are facing the environmental managers at existing and former DoD facilities, we plan this webinar, which again is innovative techniques in creating long-term solutions for large groundwater plumes. We hope this information presented will be useful in evaluating techniques that may be applicable at your sites. Following the webinar, as Nicole had indicated, you can get the presentation. Will be emailed out within 3 business days, and we'll also be sending out PDH certificates. This webinar would not be possible without our presenters, so certainly would like to thank them, and you'll get to know them a little bit more as we move forward here. I'd also like to thank each of y'all again for taking time out of your busy day to join us, and looking forward to the presentation and to your questions afterwards. I encourage you, as you have questions, to go ahead and you can type them in. We're going to have a little 5-minute Q&A after each of the presentations, and then we'll have some additional time at the end, and we'll try to address those questions as best we can. So, a little bit of background here. Many current and former defense sites have large groundwater plumes, and they're underneath critical infrastructure. We're at active facilities in many cases. We got runways, tank farms, buildings. And historically, this has limited, our ability to adequately distribute amendments or affect hydraulic control to help achieve our remediation goals. So the topics covered in this webinar are going to feature new developments related to the use of horizontal wells and hydraulic fracture propagation to create long-term solutions for large groundwater plumes. The talks will feature experts from private industry that are going to be discussing their recent experiences in deploying these technologies on large groundwater plumes under active facilities. So both of the speakers today are the guys that are out managing these efforts. They're not, sitting behind a desk. So they can speak directly to, what the pros and cons and site conditions that lend themselves to these kind of technologies. As a registered engineer and geologist, I've got over 28 years experience in site restoration activities, and I find that, my role as a technical resource is largely developing and reviewing of site closure and exit strategies. So, the issue of how does one handle a plume with a really large scale that also has infrastructure around it is something that is pretty near and dear to my heart. So, I mean, I've had a chance to do design, build O&M of the full range of physical recovery treatment technologies, ChemOx, BIO, EVI, all of the technologies. And I've had a chance to work and deploy numerous innovative distribution techniques, which include both of the techniques we'll talk about today of placing reactive material with hydraulic fracturing and the use of horizontal wells. Now, while these technologies can have a huge impact on our ability to implement remedial solutions, their success in achieving the desired outcome is really contingent on a solid conceptual site model and a thorough alternatives analysis. And I just want to share that today. I mean, it's pretty basic stuff, but what we see as we look across the DoD portfolio is there's many occasions when we don't have that good sound conceptual site model, and we select technologies or deploy them in such a way that they really don't have a chance of achieving our end game. Now, the aquifer material at the DoD sites range the full spectrum of lithologies from tight clays to coarse gravels. And the aquifer hydrostratigraphy is the most, influencing factor on the fate and transport of contaminants and on our ability to control and degrade them. However, most remedial investigations based purely on regulatory requirements don't adequately assess the source areas or the fate and transport issues. And this typically has led to inaccurate, incomplete conceptual site models, which significantly compromise the alternative analysis process. Many large plumes, which I'm sure you on the phone can, have had experience with, they're located at former and existing DoD sites, and they've been investigated, and they've been partially remediated for years. But often these remedial efforts have been in the form of interim actions or ineffective technologies, and they just haven't gotten to a real site closure end game. So many DoD agencies instituted a remedial process optimization, or RPO, review process to help identify opportunities for improvement. Now, this has been going on for 10 plus years, but what we're seeing is that at the same time they were looking into it, the Interstate Technology and Regulatory Council, ITRC, which develops a lot of templates basically and recommendations, guidelines for things. They developed an RPO guidance document back in 2004 to identify opportunities for enhanced and more efficient site remediation. And I actually participated in some of that early on, and the Air Force and some of the other DoD folks were active participants in that. And the results of those efforts, which looked at a whole lot of sites, identified several commonalities between poor performing sites. And the first was virtually all of them suffered from an incomplete or inaccurate CSM. And the second was that the technology deployed typically didn't achieve adequate capture or distribution to achieve the desired effect. And another critical element, especially when dealing with these large plumes, is that stakeholder expectations regarding reasonable timeframes and predictability of outcome must be integrated into the approach. So, this idea of a circa, 30-year timetable really is not based on fate and transport or source term dissolution or any of that. So we have to start using more quantitative tools and being more realistic in terms of how long it's going to take to, affect these plumes. So the takeaway here is that if you're an environmental manager challenged with developing an exit strategy, hopefully based on stakeholder expectations because you've been going to RAB meetings or whatever, for a large plume, we'd suggest you take the following steps. Revisit your conceptual site model, identify the important data gaps, and put together a plan to fill those. And once that's been accomplished, you can update your alternatives analysis to accomplish your goals. And since capture distribution systems have to be tailored to individual site conditions, I'd certainly encourage you to engage implementation professionals to help you identify those data gaps that are critical to evaluation design. So today, we will learn about techniques to install treatment zones with minimal impact to existing critical infrastructure, utilizing advances in the use of horizontal wells for biosparging, ISCO, and hydraulic control. In addition, we're going to learn about the use of hydraulic fracture placement of amendments to depths of over 200 feet for long-term groundwater treatment. So with that, I'd like to introduce our first speaker. Brian Yonkin is the project engineer with Directed Technologies Drilling, DTD. He received his BS and PhD degrees in civil environmental engineering from Penn State. For the past 3 years, Brian's worked on development and field management for environmental and water supply horizontal directional drilling projects. His current research focuses on screen designs for horizontal well applications, and prior to joining DTD, he taught fluid mechanics at Buckman University. And he joins us today from calling in the field from West Texas, where I understand he's working on a 2,000-foot long well, 200 feet deep. So without further ado, I'll pass the call over to Brian.
Thank you, Jim. Yes, I am currently in West Texas. I am in a rather quiet hotel room versus a noisy drilling environment, so hopefully you can all hear me just fine. Today I'd like to talk about horizontal directional drilling and how we can use the technology out there to install wells and sort of maybe look at other approaches other than that vertical approach that we are probably familiar with. As Jim mentioned, we'd like to have a conceptual site model. Where is our contaminant? Where is it going? Where did it originate from? A nice map or a model of that site is great. But then moving forward, how do we treat that? What are the techniques? How do we approach the remediation process? On the screen, I have an image of a site, and I should have a little red laser moving around here. We've got a building here, and this is actually a legacy site or contamination before the current owner. Looking at that is underneath the building. The gray areas around the perimeter are where we have put in vertical remediation projects, but how do we access underneath that building? Further complicate this, this is a building with active manufacturing, fairly clean areas, fine machine processes. How can we get our remediation efforts within that or underneath that building? You may have run across different sites where, again, inside of a building or underneath a building, how can we access or how can we get remediation efforts underneath that building? One would be commercial buildings. I say commercial buildings first because, well, we can go in there and potentially drill some monitoring wells, or vertical wells are an option, some warehouses, hangars, things like that. I think you'd have a very difficult time trying to convince a homeowner to allow a vertical rig into their basement or allow monitoring wells within their facilities or in their houses. And that's where maybe a horizontal well would be helpful coming in from the side and underneath those structures. What do we do if we have a pollution plume that would migrate underneath a road system? It's inconvenient at best to put a vertical well in the road, shutting off lanes for periods of time. Monitoring could be quite the challenge. Perhaps we come in from the side. And no, this is not a drill out in the middle of the water, but this is one of my locators following a bore path under a body of water. We can put in horizontal wells that would go underneath. In this case, this is a stormwater detention basin, so it doesn't always have water in, but it's kind of tricky to predict the storms. This happens to be in Georgia, where it can rain fairly frequently and fairly unpredictably. To put a rig in that location, try to get access vertically. So horizontal is another approach. Could also consider runways, taxiways. Landfill liners. If I would like to access underneath the landfill to remediate leaks around the landfill, the last thing I really want to do is go vertically and try to puncture the landfill liners to get down to my problem area. And rail lines, petroleum facilities, anywhere we have that critical surface infrastructure where you just can't put a vertical equipment to access that site, consider horizontal coming in from the side. Maybe we have a plume that has migrated off of our client's property. We can set up a drill rig on the property and potentially go underneath adjacent properties. Now, we still want to make sure that we have all the necessary permits and notifications for those adjacent landowners, but we're not parking equipment and excavating on adjacent properties if we can come in horizontally. The image on the screen now shows a rather large plume. What I have, the reason I have this on here is just to sort of show you the three-dimensional image of a plume. Often our plumes are long and fairly thin in depth. Generally, hydraulic conductivity is much greater horizontally versus the vertical, so you're going to have much greater range of that plume in the horizontal. This particular large plume, length 8,000 feet, width 2,000 feet, and the average thickness is only 130 feet. This is a sizable plume. However, you can get a sense of our length to thickness ratios of 62 to 1 or width to thickness ratios of 15 to 1. So just to back up a little bit, the history of horizontal environmental wells. It's been around a while. A lot of this technology originates in the oil fields. So directional drilling back in the 1930s, trying to access different oil reserves underground. Directional drilling in the 1970s, we started doing it to complete river crossings. My first recollection or first time I am familiar with the environmental application of a horizontal well is through a Department of Energy project in 1988. And over the last 30 years, we have a number of environmental remediation projects that have gone horizontal. And most of the remediation techniques that we put through vertical wells are also applicable for horizontal wells. Why use horizontal wells? Well, as we talked about in a couple slides back, what do our plumes look like? They're generally long, fairly thin in depth. If I have a long, thin plume that may be a couple feet deep, that's at 10, 20 feet below ground surface, I'm drilling that 10 to 20 feet down to put in a couple feet of screen interface with that contamination plume. If I come in horizontally, I get the depth, and then I can run a horizontal screen for hundreds of feet along that plume, and therefore putting far more screen along that prominent direction and location of that plume. And that's where fewer wells, perhaps. I can put in far more screen for the same amount of drilling coming in horizontally. Generally, a greater radius of influence, I say ROI, radius of influence, maybe we should better call it a zone of influence, as we're not, from plan view, it's not a circle necessarily coming out from our wells, but more of an oval or an elongated shape down the length of that screen. So potentially we can get more influence with that plume with the horizontal approach. Minimal site impacts. As I mentioned before, perhaps we can use fewer wells using the horizontal approach. We may have seen sites where it looks like a pincushion with all the vertical injection or extraction or monitoring wells around the sites, and then all the conveyance lines and maybe plumb them back to a common area, while we can perhaps reduce that to fewer wells with a horizontal well that has more screening section. As I mentioned before, the applications for horizontal wells, the environmental applications, are very similar to what we can do with vertical wells. We can still do the extraction, we can still provide injection, thermal treatment, and then some other ones, dewatering, things like that. So what the techniques we use for vertical drilling, we can use for horizontal. Now let's just get a little information on the types of horizontal wells that we can install. A continuous well would have two access points on the well. One where we enter the ground, and then we drill down depth along our target zone, and then curve back up and exit the ground. In this way, we can go to depths of more than 200 feet. The well I'm currently working on right now is 190 feet deep. Well lengths can be in excess of a couple thousand feet. In this approach, we drill out to the exits, and then we can pull our material back into place. And by doing this, I can put in fairly long wells, and I have access to both ends, which can be beneficial for trying to periodically clean the wells or rehabilitate the wells. And I have an animation here. I'd like to turn it over to our moderator to provide a little description of how this works. Drill bit goes down. If you look at that end, that twisting thing, that's my drill bit. When it's spinning, it generally goes straight. When it's just being pushed without turning, it will give us some steering. I may have to precondition the bore by enlarging it for larger material or just cleaning it out as I go underneath that building. And then finally, I pull that material into place. And I can control and direct the bore path in both the vertical and the horizontal. So I put the vertical steer into it, and I can also steer horizontally. If we want to have a little bit of curve, the image shown here is compressed horizontally significantly. So understand that the curves in horizontal wells are gradual curves, large curves. We don't make 9-degree bends under the ground. So think about that if you want to put in a horizontal well. And if we can advance to the next slide. The other type of well we could install is a blind completion. Perhaps our site doesn't have access, or we can't come out of the ground on the exit side. I've got room to come in on entry side. I drill down underneath in that case, the building in our example here, and then I have to pull my drill string out and install the well material. Now we can also go to depths of nearly 200 feet. However, we're generally limited a little bit more on our well length. You have to work with the soil conditions, the drilling conditions that are given to you, but generally 1,500 feet would be about as far as you can go with this. And the screen is pushed into that open borehole. If we can move to the next slide. And we'll run this animation. So here we're coming underneath the building, going horizontal. And now I am pulling my entire drill string out of the ground. And in this case, I am relying on my drilling fluid and the soil formation to keep that borehole open as I install the well material. We can also install through the drill rod, but the drill rod is limited in size to 3 or 4 inches in diameter would be the maximum diameter well we can put in there. So there are some limitations to a through rod, and that's basically if I had concerns for collapsing conditions, I could still install that well through that drill string. Let's just talk about some case studies that my company has been involved with, just to give you some ideas on how this can be used. One was several years ago, we worked at home Air Force Base in New Mexico, looking at soil excavation for remediation. So it's a fairly large area where they wanted to remove the soils, and we installed several horizontal wells to dewater that site for the excavation. And that was continuous wells, so open it back to the surface at both ends, 6-inch HDPE, so the larger the diameter of that well is, the more I can bring in for this dewatering effort. And pump more than, or nearly 30 million gallons of water out of there. We depressed the water table so that the excavation could occur, and we depressed it to 20 or 22 feet below the original water table. I don't know how many vertical wells it would take to do something like that, but this was with 2 horizontal wells. A case study at Moody Air Force Base in Georgia. We may have worked with projects using an extraction injection pairing in vertical wells. We may have seen that before. Let's just turn that on its side. Now I can do longer wells, nearly 900 feet long for 2 wells. In this particular site, there are 55 feet deep was our target zone, and about 500 feet of screen per well. These were double-ended, so we used a fiber-reinforced epoxy well material that we pulled into the ground through a double-ended well. And we can sort of see the schematic, the drawing on the side there. If I move forward, this was adjacent to the flight line, an active flight line. And throughout the drilling process, the flight line was not affected. There was no delays, interruptions due to their activities. So if we think about the sites that we work on, whether it's an airfield, an office building, a manufacturing facility, that critical infrastructure on the surface, if we can figure out a way to remediate or attack the plume under the building without interfering with those activities, the client is quite happy to go about that approach. On this particular project, there's a TCE groundwater plume. So after 5 months of, I believe, just extraction, microbes were added in the injection well, and then 3 months after that injection, so we've got the injection on one side, creating sort of a hydraulic gradient over to the extraction well, moving those microbes across the plume, and in only 3 months, you saw a significant decrease in your TCE concentrations. So before the wells went in, roughly 6,000 parts per billion, down to 1 part per billion over 8 months. And this particular site accomplished its cleanup 28 months ahead of schedule. I don't know what the original schedule was or how it was created, but maybe horizontal wells could be considered for future schedules. A case study at Muniz Air National Guard Base. This was where Jim Romer and I first worked together. Jim had an interesting project. I believe it was a diesel fuel leak that was in a sandy soil at a National Guard facility. I think from this picture, this aerial photo, it may have been traveling north towards the top of the page, and Jim schemed up a series of 6 wells, targeting the plume at 25 feet below, the well target was 25 feet below. I believe groundwater was closer to 7 to 8 feet below, but the idea was to use an air sparge system here and introduce air at a fairly low rate just to promote the biological breakdown of that fuel at this site. We used a pressure-activated well screen, so it took several PSI of overpressure, so you'd have fairly even distribution of the air along the full length of screen. I think in total there's nearly 900 feet of screen with approximately 15 or 1600 feet of overall drilling. Most of these wells were actually installed single-ended, so you see that they have connected back, my laser pointer here, back to common wellheads here, and then all conveyed back to one common central facility. Jim put together a very nice little remediation unit there that he could actually communicate with from his home office, so it's a lot easier to monitor the remediation efforts from afar. But it's a very nice project. This picture may look familiar from our webinar invite. This is a larger operation. I've got tractor trailers here. I've got large drill rod, a bigger drill rig. In the background, we are on a military base here. This is Robins Air Force Base in central Georgia. Putting in some larger wells that go hundreds of feet along. And if I go to my next picture here, you can see going right underneath the main, very active runway. We are adjacent to taxiways, and we actually, the one well on this particular image is going underneath that runway. And they were certainly flying and conducting air operations during our time down there. At no time were we interfering. We weren't putting any equipment on the runway or stopping any of their activities there. And we're putting in these 5 wells. I think we also have put in some other wells around the area. On this particular project, you're looking at over 5,000 feet of drilling and 3,000 plus feet of horizontal screen. This is a large plume underneath an area that is just not conducive to bring in vertical drilling equipment and have equipment parked out there in their airfield operations. As you can see, depths 50 to 70 feet deep. Some of these were through rod well installations where we drill out and push the well material through the rod, and some of them I believe were also double-ended. So it just varies. The soil conditions down there with some of the clays, it does change up your drilling approach for these wells. I just showed a picture before of a big rig operation. You've got multiple tractor trailers, 31-foot long rods, a drilling rig that can push and pull hundreds of thousands of pounds. Not all sites require 6 or 7 tractor trailers pulled on the site. Sometimes we're looking at a smaller target area. Here I've got a small drill rig, and really the size of a small car, put on a small trailer, driven around by a pickup truck. Right next to an active flight line. You can see the aircraft right behind us. We were certainly not the noisiest machine at times at this location, but there was a historic underground storage tank right in the middle of their taxiway in and out of their maintenance shops at this facility. And it's a little difficult to either dig a big hole at that where the concentration is or come in with vertical rigs. So we set off just the side. We're actually in the grass just off of the taxiway apron area and drilled relatively short, 160-foot long wells underneath and out to the target area. And that picture in the lower center is my marks moving out across every 10 feet length of our drill rods, doing our locates out across there so we can just sort of steer out. You see some horizontal, so I'm coming, both wells are coming from the same entry point, curving out a little bit horizontally before paralleling and going out 160 feet. I believe there's about 100 feet of screen on each one of those wells, and they were blind well installations. Here I've also tried to put a drill rig in a very small spot. We always seem to be given very small spots to set up our drilling operations. This is a slightly larger rig, but still you can see we're right up against. These are residential buildings. This is a former naval facility in California, and we needed to get some soil samples underneath these buildings. So I'd like to show here that we can access fairly small areas in between residential buildings, next to buildings, and access it. Generally, what I'd like to have is about a 5-time setback. So if my target depth in this case was 3 to 4 feet below the building slabs, I want to start back about 15 to 20 feet, enter the ground 15 to 20 feet, so that I can curve down. Again, can't make sharp turns with our drilling equipment, and get to the target depth where we want to be. So this is a former naval facility. Sample locations were approximately 50 feet in from the edge of the buildings, 3 to 4 feet below grade. This is fairly shallow. We are using a mud rotary system, or a mud system, where we are pressurizing the bore with a little bit of mud, trying to minimize the pressure, but we want to make sure that we're not allowing that drilling fluid to escape into the residential buildings. This is a big criteria for this site and most any sites, not allowing that drilling mud to migrate vertically into the surface or occupied space above. In this case, we did not do that. It was contained. We took 10 samples, and there was no impact to the residents. I don't even think they knew, other than the noise on the surface outside, there was no vibration, no indication that we were underneath their buildings. I provide my contact information. Thank you for joining us on this webinar, and if there are any questions, I'd be happy to answer those at this time.
Well, thanks a lot, Brian. I did have a couple that came through here during your presentation, and one of them is, I think, a pretty obvious one. I know the first time I saw your rigs out working, I was trying to figure out how in the world you kept a really close, tab on the vertical and horizontal location of that drilling tool. So if you could share something about that, I think that'd be good.
Sure. I'm going back to this slide just because it is the one picture I have in this presentation that shows a little bit about our navigation approach. This is, our technician here is holding in his left hand a surface locator, and this is communicating with a sonde located directly behind the drill bit. The sonde is providing information, pitch, clock face, the rotation of that drill bit, and depth of that drill bit. Generally, the documented accuracy of these devices is about 2% of the depth. So if we're at 10 feet, we're within a couple percent of the foot of our of what's reading on that box. And so we're tracking that along the bore path, roughly every 10 feet or however often we want to take those tracks. If I don't have access to the surface, I can, directly above my bore path, there are other options such as a wireline or even a gyroscopic steering tool approach where all that information is fed up through a wireline through my drill string. But what we can do is monitor the orientation of that bit and how it's tracking, whether it's tracking along the prescribed line or a little bit deviated, and we can steer back onto it. And like I said, generally within a couple percent of the margin of error on these locating devices.
Okay, yeah, no, that's pretty helpful. I know sometimes there can be interference, like with reinforcement in concrete slabs, for instance. So when you're tracking them under buildings, how do you handle that?
Thanks for bringing that up. Yes, the sound emits generally a radio frequency and an electromagnetic signal. And large steel, think steel siding on large buildings or hangars, sometimes steel reinforced concrete, large pieces of metal can interfere with that electromagnetic signal. Or an active signal such as generators, overhead power lines can also interfere with that. There are a number of different sondes which emit at different frequencies, and sometimes it's a trial and error process to get the frequency that will go through or go around those objects the best. And it's certainly a little feel for how that works. Generally best to cross perpendicular some of these passive interference locations so you don't have a prolonged interference zone. But if there's just too much surface interference, you can go to a GST or a wireline approach where you're getting all that signal from the device right behind the drill bit up through that wire to avoid the interference.
Well, we got time for one more. I think there's a couple that, you know, we're seeing longer and longer wells. And I know, like you indicated, back in the 80s, I remember people first started, you know, trying to do some horizontal wells. And some of the early challenges weren't just the drilling and installation. You deal with the screens themselves to ensure you know, even distribution. So for the example, the ones that you installed for me down in Puerto Rico where we were trying to do biosparging, we wanted to make sure that at the end of that screen interval, we were getting the same kind of airflow up into the formation as we were, you know, at the beginning. So I know that you've been working on, you know, different techniques for enhanced screens and that. If you could comment on that, that would be helpful, I think.
Sure. Yes, I've activated a slide that shows the site in Puerto Rico. These were using a pressure-activated well screen, so the slots basically in that screen stay closed as they get to pressure. So the idea is that you have fairly uniform pressure along that screen. It's really that pressure differential inside the screen versus outside the screen. Whether it's injection, where I've got greater pressure inside the screen pushing out, or I reduce the pressure inside that screen for extraction. Generally, so you've got that pressure differential, and the further you move down that well, the less pressure you're going to have, or the less pressure differential you will have. And that's due to just the fluid moving down the well, frictional losses as you're moving down that well. You can correct that. One would be to use a larger well, and that would reduce your frictional losses along that well. But if you look at it over 100 feet or a couple hundred feet, your pressure losses at the fairly low injection rates or airflow rates that we're talking about, there's a a fairly small pressure loss, fairly insignificant pressure loss along that screen. If I get to much longer screens, hundreds to 1,000 feet long, then yes, that becomes more critical, in which case we may want to consider putting several different screen openings, open area percentage would be a parameter to use, where you have less open area at the start of your screen where you have a little bit higher pressure, and increase your open area as you go farther down. Ideally, we can have a continuously varying screen opening, but realistically, that's a little hard to manufacture or keep consistent in the field. Having said all that, it really comes down to the formation itself and making sure you have a good understanding of the formation and what the hydraulic conductivity or pneumatic conductivity you're trying to force this material through.
No, those are all good points, and I know, of course, one question everybody's always got is cost comparisons to, you know, other approaches. Now, I think in a lot of these examples that we've shown, it's not even an option in many cases to install enough vertical well points to affect the same hydraulic capture or injection area that you could achieve with a horizontal one. But what are some of the, I know there's a range of cost, obviously depth and size of boring, and there's a lot of factors, but just for people who are, you know, looking at, say, an application where we're looking at that 50 to 80 foot depth maybe, and, you know, they're looking at maybe 300, 400, 500 foot long wells. I mean, what kind of range of costs would you provide them for just, you know, conceptual purposes?
There's a lot of factors involved there. Generally, we're remediating in our sand silts, which are fairly easy drilling conditions. Once I start drilling in rock, worst case scenario is cobbles. You're moving along just fine in sands and silts, and all of a sudden you hit a big rock or a cobble that sort of deflects you or prevents you from moving forward. I have to start over again. So it's very site dependent. I think I'd have to evaluate each site to give an idea. I will say that per foot, generally, horizontal drilling is more expensive than vertical. However, some sites just don't allow that vertical access, or I can put more screen per overall length of drilling that I do. That's over, if you look at a big project or a project where you sum up all of your vertical wells, fewer horizontal wells, while the initial cost is higher, would come down to a competitive level.
Yeah. No, I understand. I think that really, again, sort of highlights the need for, in your conceptual site model, as you're, you know, looking at certain technologies you may want to evaluate for your site, it's really critical to reach out and talk to those folks and understand what lithologies and situations really drive the cost. Because in many cases, you know, they're not appropriate, you know, for the application. So anyway, Brian, I sure appreciate your input. And again, you've got his contact information, so I'd certainly encourage anybody to reach out.
And I would say that the drilling companies that specialize in horizontal remediation wells have the expertise and the staff, professional geologists and engineers that can help with the horizontal well possibility. So like I said, I can't give you a cost without looking at it further, but we have the expertise to help evaluate your sites.
Okay, great. Well, we appreciate it. So now I'd like to move on and introduce our second speaker today. You know, we talked about big plumes and different approaches, and so a lot of what Brian was talking about is really a dynamic approach where you're either capturing fluids or injecting fluids, and so you're installing the conveyance, you know, structure, the horizontal well, and then you operate it. You're going to have some infrastructure associated with, again, injecting fluids or extracting and possible treatment. on some of these larger plumes, and the chlorinated solvents is a classic example where we try to take advantage of technologies like ZVI or, reductive dechlorination. There's amendments that need to be gotten in the ground, but then if they're chosen and applied correctly, you may not have to do anything for several years. So now the question is, how can I take, it's one thing to take a liquid and put it in the ground. What if I'm trying to get something that's more of a solid that's going to last multiple years like a ZVI? And that's sort of the sweet spot, I think, for the hydraulic fracture placement of those kind of materials. So I'd like to introduce our second speaker today, Doug Knight, who is currently the Vice President of Operations for FRX, but don't let that title fool you, because I see him out in dirty jeans and boots all the time on my sites. So after obtaining a BS degree in environmental engineering from Clemson, where a lot of this technology actually has been developed, he spent 5 years in environmental consulting, and then in 2000 he joined FRX and has spent the last 17 years injecting fluids into the subsurface for the purpose of remediating groundwater. I know he's completed over 1,000 fractures, including work at many DOD sites. He now functions as an injection consultant in designing remediation projects for FRX's customers, and I've actually been working with them on a site that we'll look at a little bit more closely. When I was asked to put a webinar on, I told him I didn't take that lightly and don't like to pass along information unless I've had an opportunity to directly observe it. And so both of these speakers today are, like I said, very experienced in actually doing this in the field. So welcome, Doug.
Well, thank you, Jim. Excuse me. I appreciate the introduction. My talk today is, in fact, about horizontal fractures used for the remediation of groundwater. And I'm going to repeat a lot of the words we've already heard because we're really focused on the horizontal. Similar to horizontal drilling, we're in the business of horizontal fracturing. Excuse me. So I will skip my my first slide. That is, whoops, how do you do that? The introduction of myself, which we've already covered. So my talk today is in 3 sections. The first section is a justification for why we feel that we view the problems in our industry as horizontal problems, and which is why we think we need horizontal solutions for these problems. The second part of the talk is the science behind fracturing. This is from the origins to the technology today. It's the science of fracturing. The third part of the talk will cover a couple of real-world sites that we've been working on recently and currently. So to get into the first part of the talk, this is the concept that the problems are horizontal. So kind of as was already covered in the first talk today, just a repeat of that information, contaminants in the ground are transported to a greater degree laterally than they are vertically. In my experience, I see sites that are typically measured in the tens of feet in the vertical. Maybe sometimes I've seen a couple that were more than 100 or 200 feet, but it's quite rare. Most of the problems are in the horizontal are definitely measured in the hundreds of feet, thousands of feet, miles, and definitely acres. And we are focused on those large plumes in our talk today. So a couple of examples of those. This is a DOD facility. It's in Wyoming. I've labeled one of the 4 plumes with the letter A at the top of the slide here, and just as a representative example of this plume is about 6 acres in footprint, but it's only about 50 feet thick. So the vertical component of a contaminant plume, it is important. You have to treat it, but to a relative degree, I view this as a horizontal problem. And the next site shows the same. This is a private manufacturing facility in South Carolina. It is of similar thickness as the first one. It's about 60 feet thick. I think at the maximum, it's about 60 feet thick. This one happens to occupy over 15 acres of property. So again, we're viewing this as a horizontal problem. So to attack these large plumes is maybe somewhat obvious to most of us here, but the techniques that are used to remediate groundwater have a cost associated with them. And when you want to apply them to a large plume, then you just simply have to multiply that cost across that entire plume. And those costs can quickly get out of hand and start to make things not feasible. These are all of the typical remediation techniques used on small plumes, obviously, are used on large plumes. So a way to try to deploy some of these techniques on a large plume, similar to one option you might have is using horizontal drilling techniques. Well, we also offer horizontal fracturing techniques. So the cartoon on the right is meant to show the emplacement of horizontal fractures in the subsurface with a broad extent measured in the tens of feet and on occasion maybe more than 100 feet. It has been done. It is currently being done, but more typically it's measured in the tens of feet. The vertical component of a contaminant plume would be handled by the stacking of these horizontal features in the vertical. So my cartoon is showing 3 fractures that were stacked vertically in this given location. But the major component of these fractures is in the horizontal, the lateral. So these structures can contain thousands of pounds of reactive material in a single fracture. So we're talking about emplacing material in the ground real fast, not meaning that we're pumping fast, but a single fracture can take many thousands of pounds. So a couple of other benefits are represented more in the map view, kind of restating that a horizontal fracture with a radius measured in tens of feet, it should be relatively obvious that you would need less wells to cover a given area as compared to a conventional injection technique that might be a direct push and pump event, and it could also be a fracturing event that's not in the horizontal. And I'll get to that later in the talk. So they should require less wells to cover a given area, and they also can propagate beneath buildings. So there's no limit there, so you can get access under a building without disturbing that building. So to finish up this first section of this talk, I'll just throw out there quickly that this technology, this technique of creating horizontal fractures, it applies to any subsurface formation, whether it be solid granite bedrock to beach sands that flow up into your wells. All of these materials can be fractured because they all do in fact have structure that when fluid pressure is applied to it, they will fracture. It can be used with any drilling technique, at least any that I've ever heard of, we have worked with, from direct push to sonic to any type of drilling technique. At any depths really, except I've actually only been to a maximum so far of about 200 feet. And again, that's where we see most of the environmental problems anyway, and we haven't been asked to go deeper. And of course, any amendment type. If we're trying to put in reactive material into the subsurface, it doesn't matter if that material is a solid, a liquid, or a gas, it can be incorporated into the fracturing techniques. So the next section is about the science behind what we're doing with hydraulic fracturing. The science was worked out in the late 1980s when the EPA funded some research at the University of Cincinnati. And that's where 2 individuals, Dr. Murdoch and Dr. Slack, got together and ran a laboratory on behalf of the EPA for the better part of a decade and spent a few $1 million of research money sorting out the techniques and benefits processes of creating horizontal hydraulic fractures for the purpose of remediating soils and groundwater. At the end of that research, the EPA encouraged them to commercialize it, to start a company. So they did and have been in that business ever since. So the company focuses on horizontal hydraulic fracturing. So what that is, what a hydraulic fracture is. When fluid pressure is applied to the subsurface, soils, rock, whatever it may be, when fluid pressure is applied to an extent that exceeds the strength of that material will fail. It will cause a mechanical failure. That failure is in a is in a planar form. The orientation of that plane can vary. It could be vertical, it could be horizontal, and sometimes it can be a combination, but not usually. So I'm going to repeat what I just said in different terms. When you pump material into the ground too fast, the ground's going to break. And when it breaks, it's going to make a plane, a single plane. And that plane could be in the horizontal, which can be quite useful to us, or it could be in the vertical, which is almost always not very useful to us. I need to describe here why we're looking at containers of Jello. This is a phase of research that we conduct at FRX where we create fractures in gelatin because they're easy to visualize and we're able to recreate some site conditions using gelatin. Now, there are a lot that we cannot recreate, obviously, but there are several that we can. So the first two pictures on the left are of the same container at a slightly different angle so that we can have perspective looking at it. The vertical blue line, it was the borehole that was inserted into the gelatin. Fluid pressure was applied, and a hydraulic fracture resulted from that. This fracture happens to be horizontal because steps were taken to make it horizontal. The picture on the right, if you can see, have perspective looking at it, I wish I had a video, but I don't. That's a vertical fracture, or a mostly vertical fracture. It was created using almost the same techniques, except no effort was made to dictate the fracture orientation, being vertical versus horizontal. No effort was made, and the result happened to be vertical in that particular sample. And I'll show you some more of those later. There's a couple more points to make about fractures are planar features that can be oriented in different directions, but what they cannot be. They are not dendritic patterns. They are not spiderweb shapes. They are not shattered soil or rock. It is not possible to create these types of features in soil or rock by the application of fluid pressure. The photograph that I have here does accurately photograph stained, dyed patterns of spiderweb fractures in the subsurface. These are real, but these are natural. These were already there. These were not created. It is not an option to create that type of fracture pattern in the subsurface. Another option that is not possible is the creation of a blob. Maybe most of us can assume that intuitively, but it has been asked of me several times. It would just simply take too much force to try to push soil particles away from each other in all directions at the same time. That's not how the soil fails. That's not the failure mode of the structure. So they are planar features. So I have another Jello sample here. This is a container in which we created about 8 or 9 fractures. So each little wing you see there was an individual fracture that was created by applying fluid pressure. The fluid, in this case, was Hershey's chocolate syrup that was injected into the gelatin. So we created a borehole and we created a fracture. And then we advanced the borehole and created another one. We advanced and created another. With no steps taken to dictate the orientation of those fractures, you can see we got varying results. The one at the top is vertical, and you can see, maybe you can see that it actually made it to the surface. It daylighted or vented to the surface, and a lot of the chocolate came out of the fracture. The next ones down, some were horizontal, some were vertical, and you can get different results depending on different depths, different conditions in the ground, unless these conditions are controlled. So the next image I want to show you is we do have the ability to control this. We can make fractures horizontal. We have to use certain equipment, tools, and processes to do so, and you have to have a good understanding of what drives it. So the image on the right is the creation of a stack of 4 different horizontal fractures created from fluid pressure. So what does control it? These are the items that you have to pay attention to when you want to control if a fracture is vertical or horizontal. I will note that it's relatively easy to create a fracture in the subsurface. You turn a pump on and you pump it harder or faster than the ground can take it. A fracture will form. However, creating them in the horizontal takes a lot of specific steps and attention. A couple of which I'll highlight here are the composition of the slurry. The material that we're pumping into the ground is very important. It's thickness, its viscosity, its cohesion, the solids, liquids components, the ratios between the two. These are very important. And to give you an idea, to create a fracture with just water, it's very difficult to create a horizontal controlled fracture with water. It's too thin. And to go beyond that, to create pneumatically induced fractures, such as with gases, it's very hard to control that fracture and make it a horizontal form. It's easy to make a fracture. It's just hard to make a horizontal one. The stresses in the soil, these are natural conditions. These play a big role in the creation of the fracture, and they can actually be controlled. They can actually be changed. The pressures that we use to inject, I find that this is one of the most asked questions, and one of the more surprising answers that people hear from us is that it doesn't take much pressure to create horizontal fractures. It does take a lot of pressure to create vertical fractures. So once we have created the conditions that favor a horizontal fracture, then we would expect relatively low pressures to create that fracture. And if we were to see high pressures, then we now know that we have failed to create the conditions for a horizontal fracture. So high pressures are an indicator that we have not done our job right. And I'll cover that again in a second. The act of drilling a hole in the ground and using packers also play a role in dictating the orientation of a fracture and the geometry of that borehole. This one I have a graphic to show because it's one of the simpler ones to explain, that when we create a vertical borehole in the ground, we have created a shape that is a cylinder. When we pressurize a cylinder, the failure mode of that cylinder is along the long axis, which is parallel with that cylinder. So with a well bore, that is a vertical line, and I'll show this image here because it helps explain a good bit. So this water pipe was overpressurized from the inside until it failed. So what we see in this image is a vertical fracture. So I think this is a beautiful image of a vertical fracture, which is usually not what we want to create in the environmental field. There's a couple of things that don't really play much of a role in whether a fracture be vertical or horizontal. The bedding planes of sedimentary rock and the relic fabric and structure that comes from the parent rock that can be in soils, it doesn't play as big of a role as we might think, because once we take control of all of the other factors that I explained on the last slide, these things become minor components. They can be overcome quite readily and don't really dictate where the fracture is going to go. And I will also mention this bottom picture here is something that cannot be done. You cannot drive a fracture in a given direction, meaning if we put an injection tool in the ground and activate and pump through that tool, and it has an opening pointed to, I will pick a direction and say to the west, you cannot create a fracture that propagates only to the west. These fractures are planar features that propagate in 360 degrees. So that is not one of our options for making fractures. And just so in concluding this, I like to see this image again, because on the left, There were fluid rheology problems. There was borehole geometry problems, and the pressures were higher than they needed to be in some cases, and these fractures were not controlled. In the image on the right, we intentionally controlled all of these fractures and got the result that we wanted. So in the field, we need to know after the fact, beyond the science in the laboratory, we need to know, did we get what we wanted? Did we get horizontal fractures? So it starts with the science that we brought to the field, the techniques and the tools to create horizontal fractures. That's where it starts. Then we can go on and do some other things such as excavating these fractures, taking core samples. We can measure any displacement of the ground surface. This applies mostly on shallow sites. We look at the injection pressure I mentioned earlier. It needs to be low. And one obvious indicator of a vertical fracture is daylighting or venting, which some of you might have seen on some of your projects. When material comes up out of the ground, that's quite obviously, at least to me, that's a vertical fracture. So some examples. These are excavations. These are pretty much exclusively for research because we don't dig into contaminated sites like this. The far left is a site in northern Europe where we created a fracture horizontally with a white sand that you can just see at the bottom there. The picture in the middle was actually one of the original research projects for the EPA. This is in the upper Midwest, a glacial till clay material. And you can't see very well in the picture, but there are 3 horizontal fracture lenses in the sidewall of that trench that we've dug. The one on the far right is a site in South Carolina. It's in Piedmont saprolite soils. And there's another one here that is also in Piedmont saprolite. It's a different site, but it's another one we did. And this one was very highly measured on the sub-centimeter scale. Every part of this fracture was measured and mapped. And this was actually published in a journal, I think in 2012. We do these excavations about once a year or so. Generally, we're participating with university research, but another method is coring. This is something you can actually bring to your contaminated field project. We can take cores, and you can see the fractures in the cores. The picture on the left is a split spoon sample. I use this picture because it's quite obvious that there is a very colorful material that happens to be potassium permanganate, and it is diffusing into the soil on the sides of the fracture lens, but it's just meant to illustrate that core samples can show fractures. The image on the right is another core that is broken at the fracture, again showing that we can core for these things. This is a photograph of a vented or daylighted fracture injection event. This fracture was a research item where we were working on some different concepts, but the result of it was a vertical fracture. And when we have daylighting on our project sites, when you see that, that's a vertical fracture form, and usually, almost always, undesirable. Another way of measuring fractures in the field is measuring the displacement of the ground surface. We do this with traditional surveying equipment. This is a total station laser system for measuring movements of the ground surface. These are typically sub-millimeter scale. There's not a lot of movement, but they can be, if you work quite shallow, they can be a couple or a few millimeters, and it allows us to make predictions of where the fracture is below the ground, assuming that the ground above, any ground that moves is probably above the fracture. It's kind of a way to rough out where you think the fracture might be. And getting back to the pressure. In general, if you create the conditions that are appropriate for a horizontal fracture, it does not require much pressure to create that fracture. If you find yourself creating a larger pressure in the probably anything more than the 200 to 300 PSI range, then it's a good indication that you didn't meet all the conditions for making a horizontal fracture, and you're probably making a vertical fracture. This image here, this is a pressure log that we take on each and every fracture we've ever created. This is pressure over time graphed, and a couple of key pieces here about this graph is this is not a cartoon. This was not created for this presentation. This is just simply the last pressure log we collected. This was just a couple of days ago at a site in Colorado. This is a fracture that was created about 25 feet below ground in a tight clay formation. And I'll point out that on the left-hand side, the highest pressure you see on this graph is 80 psi. And so I'm stressing it's relatively low pressure work. There's another key feature at the beginning of the event where you can see the break, where the soil failed. The soil failed at about 35 psi. And I don't have my pointer turned on right now, but that's what's happening at the very beginning. All of the rest of the information in this graph is incredibly interesting to me, but maybe not to you. So I will move on to the third part of the talk. Just want to tell you about some of our real world experiences, some stuff we're working on these days, and kind of show you some of our equipment. I think I have an image that failed to load here, but it was actually a picture of our equipment, our frac rig. There are some other pictures here in the center and on the right that show some of the typical drilling equipment that we use. Excuse me. The pictures on the far right are to demonstrate the slurry that we're injecting into the ground. Again, so you can see that this stuff is quite thick in most cases, and the properties of that slurry are very important to the fracturing process if you intend to control that fracture. Here's a good overview picture of our equipment. This is a site in Cheyenne, Wyoming. It is the project that we were working on most recently with Jim Romer. It's a former DOD, and this is just meant to demonstrate the footprint of what we look like in the field. We use a few pickup trucks and tow a few trailers, and the equipment comes from that. We make this equipment, we manufacture it ourselves. It is custom built for the purpose of mixing and injecting. So that site that we were just looking at, it has a total footprint of probably more than 14 acres or so. It is relatively deep, and well, relatively, it's the deepest work we've done to date. We are working upwards of 200 feet. So it's chlorinated solvents, and we were primarily using ZVI, although there were some other materials that were injected. It's primarily a zero valent iron, or ZVI project. We are injecting greater than 1 million pounds of this material in fractures that we're creating at depths of up to 200 feet. These are some of the largest fractures we've ever created. These are the largest fractures. A typical fracture on the project contains more than 10,000 pounds of ZVI in a single fracture. And we had the opportunity to see if we can make them a little bigger. And the biggest fracture created on the site, it was greater than 20,000 pounds of ZVI into a single fracture. And to give you an idea, that's an entire tractor-trailer truckload of ZVI. That's one whole truck injected in one event into one fracture. A couple of the challenges on the site, given its depth, and also the soils were somewhat cemented in some layers, so the ground was a bit hard in some places. So we had to modify our techniques a little bit, and it goes back to these, I keep calling them the conditions that have to be right for creating horizontal fractures. Sometimes we have to make slight changes to those given site conditions. So we had to work a little bit on our borehole geometry on this project, given that the ground was a little bit hard. It was deep also, which made us have to pay a little bit of attention to and make some changes to our slurry composition. So the physical properties of our slurry had to be modified slightly in order to achieve this project. I don't have it listed here, but we were able to verify through multiple lines of evidence and enough to convince ourselves, certainly, that we're creating fractures with tens of thousands of pounds of material that have a radial distance of greater than 50 feet. So we're talking about a diameter that exceeds 100 feet on these fractures, and we have a few different lines of evidence for that. It's a little hard to go and take core samples at a site like this when one core sample would probably cost you $20,000. So that could be a little tough to do. Oops, wrong button. So the next site we'll talk about is another DoD site. It's also a very large plume. This one's in the southwest. This was a TCE and a 1,4-dioxane problem. I wanted to talk about this site because it illustrates the importance of slurry composition in conjunction with the amendments, the remediation materials that need to go in the ground. The list of ingredients, the recipe for these fractures, is on the right-hand side of this slide. There are many ingredients here. Some of these are solids. There are a couple of the different ones that are solids. A few of them are liquids. One of them is actually a gas that was infused or dissolved into water to make a liquid. But we have solids, liquids, and gases on the right-hand column, that all of which went into each and every fracture. So a single fracture received this combination of materials, and we had to spend some time working on the slurry that was going to be able to carry these materials, not chemically interact with them in a negative way, and put them in the ground. So we spent a lot of effort creating the appropriate carrying system or slurry system for injecting these materials. And we did, and we proceeded to create several hundred fractures for this project. And I will move on to the last kind of case study. These are more just kind of highlights of some sites we've done. This one is not DoD, but it's a private industry site. It's on the East Coast. It's a very large plume. It's greater than 25 acres. And it was contaminated with metals. So the solution that was chosen by our customers was a pH adjustment for fixation of the metals in the ground. And they chose a product called MGO. This is, I apologize for that noise. EnviroBlend is the product that we were putting in the ground. And the ground itself was composed of sand. These were grading fine to coarse sands with depth, but it was very shallow. It was only 12 to 25 feet or so. So we have a flowing sand condition, and we have what was determined to be greater than 1 million pounds of this EnviroBlend material that needed to go in the ground. So as much as possible each time is the goal. So a horizontal hydraulic fracture is necessary to achieve that. So we had to modify our efforts to change the in situ stresses of the formation. And we did this. It took us about a week to sort out how we were going to do it, but we were able to change that. We were able to overcome the fact that the flowing sands you might consider don't have structure. However, they do. They do have enough structure to induce a fracture plane into. So after about a week's time, we sorted it out, and then we spent the next couple of months injecting this material throughout the project with several hundred fractures. So I'll conclude. From our perspective, we view large plumes as a horizontal problem, and we consider that they need a horizontal solution, such as fracturing or horizontal drilling. We think, obviously, that fractures are a great solution to a lot of these sites. And the most important point of the talk is these fractures need to be horizontal, and they can be made to be horizontal. It can be controlled. We can do it on purpose, and we can create horizontal fractures for the purpose of remediating sites. And that's the end of my talk. I'd be glad to answer some questions, and I'll turn that to you, Jim.
Oh, that was good. Yeah, this has been an evolving process with larger and deeper sites with more and different types of amendments. So it's great to see an update of where we're at right now. But one thing I want to make sure everybody appreciates is when you look at one of the really long plumes, thousands of feet long, you can take a technology like this and you don't have to basically carpet bomb the entire plume, because it just, from a cost standpoint, would be prohibitive. But you can put in parallel treatment zones with these technologies that are oriented perpendicular to the groundwater flow. And so you can have several of those, and the spacings obviously dependent on your groundwater flow velocities and how long you want to basically take to clean your plume up. But you can, configure these in such a way that, you don't have to cover the entire plume. You can also put something like this at the leading edge of your plume in place of something like an active pump and treat system, which obviously from an O&M standpoint can be challenging. And you can also inject not reactive material, but you can actually create and propagate that fracture with sand, which if you're in a tight, like saprolitic silt or something with a 10 to the minus third or some kind of fairly low K value, that sand lens now has a much higher K value, and actually you can create a well that pierces those horizontal planes you've created, and you can use them to then distribute a liquid reagent, or conversely to try to remove liquid. So a lot of neat applications. So I guess, Doug, I'd like to ask you, because I know for myself, one of the bigger challenges as a manager of a project like this is going to the regulator and saying you're going to use frac, and you get about that much of the word out, and they're immediately thinking of the, gas and oil shale play, fracking. So real quick, what's your response? I know you talked about lower pressure and much more control, but how do y'all answer that question? And if you're talking to somebody who's got a project, what kind of information as they complete their conceptual site model would you really like to see?
I'll answer that in reverse. The questions or the information I'm looking for when we're going to start talking about a new project are what type of drilling is required to get into the ground. So it could be any from direct push to sonic. It could be a horizontal drilling technique, although we haven't tried that yet. So what type of drilling is going to dictate what type of techniques I bring to the project? I need to know the nature of the material. We do work in solid granite bedrock. We do also work in flowing sands, as I discussed. So, and obviously tight clays. Tight clays is most of what our work is. So those are the first two key pieces of information that I need to know. And what your approach is. What are your goals? Are you trying to extract? Are you trying to inject? Are you trying to make a barrier wall effect, or something else? The regulator question with the negative press on hydraulic fracturing from the oil and gas industry, to be quite frank about it, I try to stay as far away from it as I can. In some states, we actually just simply don't use the words. We start to call it environmental injections and things like that in our paperwork. And it's not meant to deceive or mislead, but it's not against the rules. So it's just a kind of a reaction from some individuals that you just don't want to have to deal with. It's obviously very different. The oil and gas people are working with significantly higher pressures at significantly deeper depths, and they're dealing with different types of problems that we are. We're not really dealing with the problem of potentially contaminating something. We're there because it's already contaminated. So that's mostly understood by our customers and regulators.
Well, sort of a follow-on to that, which is one of the questions that was sent in, is do fractures pose a danger to surface structures or buildings?
Right. The short answer is no, but there is a yes to the answer. We work at depths where the groundwater is usually, and once we get deeper than 10 feet, and then certainly deeper than that, there's no concern at all, because when that crack is opened, it's going to lift the entire overburden block above it. And when it does, it's going to also compress it a little bit. So it's hard to even detect that the ground has moved once you're injecting below, say, 10 feet. If we were asked to inject beneath a very sensitive structure, and my example is a historical building in downtown Atlanta that was of great value to the community, they asked if we would be willing to fracture inject beneath the building at 2 feet. And we had to decline. There's no way I would try to do something like that. I don't even know if it would hurt the building, but I wouldn't do it. So even if the ground surface does move, it's on the order of a millimeter or sub-millimeter or maybe a couple of millimeters. But all buildings are built to withstand that type of differential movement. You're not going to, it would take more than that to even crack sheetrock or plaster.
Right.
So that was the longer-winded version of the answer.
Well, no, that's very helpful. And again, I want to thank you for your presentation, and I'd certainly like to extend a warm thank you to all of our attendees as well. And on behalf of the Society of American Military Engineers Environmental Committee, we appreciate everybody's participation. Hope this webinar has been useful. And if you've got any additional questions, please submit them via email to Nicole Matthews at nmatthews@sami.org. And with that, this concludes the webinar, and you can disconnect, and I hope you have a wonderful day.
Thanks, everyone.